Hello there, welcome to the Science Owl Station channel. Today we begin a quiet journey alongside something that never truly rests, something that has been traveling long before you or I ever existed. We're following light itself, soft, tireless, ancient, moving patiently through the vast darkness of space. Imagine yourself floating gently beneath a night sky, the air calm, the world slowed to a whisper, as countless faint signals drift toward you from unimaginable distances. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel like it, let me know in the comments where you are and what time it is for you right now as you listen. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. We often speak of light as if it arrives instantly, as though the moment something shines, it is immediately seen. But light does not rush. It does not teleport, travels, always at the same unchanging pace, step by step through the fabric of space. Even the light filling the room around you right now has spent a tiny fraction of time crossing the distance from its source to your eyes. On Earth, that delay is imperceptible. In space, it becomes the entire story. When you look up at the night sky, you are not seeing things as they are. You are seeing things as they were. Each star, each faint glow, is a preserved moment drifting forward in time. The sky becomes a museum, not built of stone and glass, but of photons, ancient messengers carrying records of long-past events. Some of the light entering your eyes tonight began its journey before human civilization existed. Some before Earth itself had cooled. Light speed is astonishing yet limited. It moves at exactly 299,792,458 meters per second. Not approximately, not roughly, exactly. This number is so fundamental that scientists have built our very definition of distance around it. A meter in modern physics is defined by how far light travels in a fraction of a second. Space itself bows to light's rhythm. And yet, even at this immense speed, light takes time. If the sun were to suddenly vanish, quietly, impossibly, you would not know right away. For 8 minutes and 20 seconds, daylight would continue as if nothing had changed. Birds would sing, shadows would move, the world would remain warm and bright, unaware that its source was already gone. Only after those minutes passed would darkness arrive, carrying the truth. This delay is not a flaw. It is a gift. It allows the universe to tell its story. Light is not merely brightness, it is information. Every photon carries with it the conditions of the place it was born. Temperature, motion, composition, violence or calm. Light remembers. When a star shines, its light records the nuclear reactions at its core. When a galaxy glows, its light encodes the movement of billions of stars swirling together. Even faint light, barely distinguishable from darkness, is rich with detail, waiting to be decoded by careful instruments and patient minds. Think of light as a letter written long ago, finally arriving at its destination. Some letters are brief, others have traveled for billions of years, crossing expanding space, slipping past clouds of dust, skimming the edges of gravity wells. Many never arrive at all, but the ones that do reach us intact bring whispers from places we will never touch. In space, nothing is truly still. and light is always moving forward. It does not slow down from exhaustion. It does not age in the way we do. From light's own perspective, if such a thing could be imagined, no time passes at all. The moment it is created is the moment it is absorbed, an eternal instant stretched across the universe. This is why light becomes our primary tool for understanding reality beyond Earth. We cannot reach the stars. We cannot visit distant galaxies, but we can listen to their light carefully, quietly, over long periods of time. Each photon that reaches a telescope has survived an extraordinary journey, and its survival alone is meaningful. Even darkness is shaped by light. Shadows exist only because light travels in straight lines. The night sky appears black not because space is empty, but because much of the universe's light has not had enough time to reach us yet. There are regions so distant that their light is still on its way, quietly crossing the cosmic ocean. When you gaze upward, you are not peering into emptiness. You are standing at the shoreline of time, watching waves of ancient brightness gently arrive. Some are strong, some are barely there. All of them are real. Light does not choose its audience. It simply travels. It leaves stars without knowing whether it will ever be seen, passes planets without stopping. It crosses galaxies that may already be gone. And yet, eventually, a few precious particles arrive, landing softly on your eyes, triggering a tiny electrical signal in your brain, creating awareness. In that sense, seeing is an act of connection across time. Your consciousness briefly intersects with events that happened far away and long ago. The universe reaches out, not with sound or touch, but with light, and you receive it without effort. As we move forward in this journey, we'll follow these travelers deeper into space and deeper into meaning. We'll see how light defines limits, bends under gravity, stretches with time, and quietly reveals the structure of everything that exists. But here, at the beginning, it's enough to remember this simple truth. Nothing you see in the night sky is happening now. Everything is a memory, a beautifully preserved one, carried patiently to you at the fastest speed nature allows. And as you rest, breathing slowly, letting your thoughts soften, remember that light has been doing this far longer than we have, traveling, remembering, arriving without urgency, without sound, without rest. Once we accept that light takes time to arrive, another idea gently settles in beside it. Nothing in the universe is faster. No matter how powerful the explosion, how extreme the environment, or how determined the traveler, the speed of light stands quietly undefeated. It is not simply a record holder. It is a boundary written into reality itself. Everything else must obey it. You can add more energy to a particle, push it harder, accelerate it for years, even centuries, and it will respond, at first eagerly, then more reluctantly. The closer it gets to light speed, the heavier it becomes, not in weight, but in resistance. Space itself seems to say, that's far enough. Light alone moves freely at this ultimate pace, not because it is privileged, but because it has no rest mass to slow it down. This limit shapes how the universe communicates. Events do not ripple outward instantly. Information travels no faster than light allows. When a star explodes, the shockwave of brightness spreads outward like a silent announcement, reaching nearby systems first, distant ones later. There is no cosmic shortcut, no hidden lane where news travels faster. The universe values patience. Because of this, astronomers needed a way to describe immense distances using light itself as a ruler. That's where the light year appears, not as time, but as distance. 1 light year is how far light travels in a single year, moving endlessly at its fixed speed, nearly 10 trillion kilometers. And yet, in cosmic terms, that is still a modest step. Our nearest neighboring star system is over 4 light years away. The center of our galaxy lies about 100,000 light years from one edge to the other. When we say these numbers softly, they sound almost gentle. But each one represents years, decades, millennia of uninterrupted travel for a single particle of light. Now imagine something trying to chase that particle. According to Einstein's theory of special relativity, as an object accelerates toward light speed, time itself begins to behave strangely. For an outside observer, clocks on board the fast-moving object tick more slowly. Processes stretch. Moments lengthen. The traveler experiences less time than those left behind. This is not an illusion. It has been measured, confirmed, and quietly accepted as fact. Time slows down near light speed not because time is fragile, but because space and time are woven together. Push hard enough on one, and the other responds. The faster you move through space, the less freedom you have to move through time. Light, moving at its maximum pace, experiences no passage of time at all. And yet, even with unlimited energy, massive objects can never quite catch up. As they approach light speed, their energy requirements rise sharply, climbing toward infinity. The final fraction, 99.9%, 99.99%, 99.999%, comes at an enormous cost. Nature does not forbid the attempt, but it never allows completion. Light, meanwhile, needs no effort. It simply exists in motion. This difference reveals something subtle and beautiful. Light is not fast because it tries to be. It is fast because it has no alternative. Motion is its natural state. Stillness is not an option. From the moment a photon is created, it moves through vacuum, through dust, through fields of gravity until something absorbs it. This cosmic speed limit also means that cause and effect remain intact. Without it, the universe would unravel into contradictions. Events could influence their own past. Consequences might arrive before causes. The quiet order of reality depends on light's restraint. Even the most ambitious dreams of travel must respect this boundary. We can imagine vessels approaching near light speeds, stretching time, compressing distances for those on board. But the limit remains. One can approach it forever without crossing. And so, the universe feels vast not because space is cruel, but because light insists on fairness. Everyone, everything must wait their turn. As you rest now, breathing evenly, imagine these invisible limits not as barriers, but as gentle guardrails, keeping the universe coherent, stable, understandable. Light does not rush, sets the pace. Everything else simply follows. In the next stretch of our journey, we'll see how even light, despite its speed, faces obstacles, bends, dims, and struggles as it moves through the space between stars. For now, let that idea settle softly. The fastest thing that exists still takes its time. Even at its remarkable speed, light does not travel through an empty, effortless void. Space may appear black and silent, but it is far from nothing. Between the stars lies a thin, ghostly mixture of particles, fields, and forces that quietly shape every beam passing through. Light's journey is long not only because of distance, but because of what it must pass through along the way. Gravity is the first great sculptor. Massive objects, stars, galaxies, clusters, do not simply sit in space. They curve it, and when light moves through this curved space-time, it follows the bend. The path of a photon gently arcs, not because it is pulled in the traditional sense, but because the geometry beneath it has shifted. This phenomenon, known as gravitational lensing, allows distant galaxies to appear stretched, multiplied, or magnified, as if viewed through a cosmic piece of glass. Sometimes the bending is subtle, other times it is dramatic. Entire galaxies can be hidden behind massive clusters, their light redirected toward us from paths it never would have taken otherwise. In this way, gravity does not block light. It reroutes it, quietly guiding ancient photons across new routes in the universe. Dust presents a different kind of challenge. Tiny grains, no larger than smoke particles, float between stars, formed from the remnants of ancient explosions. Individually insignificant, together they form vast clouds that dim passing light. As photons collide with this dust, some are scattered away, others absorbed and re-emitted. The result is a gradual fading and reddening of distant stars, a cosmic filter that alters the message light carries. This reddening happens because shorter wavelengths, blues and violets, scatter more easily than longer reds. By the time the light reaches us, much of its blue energy has been stripped away, leaving a warmer, softer glow. Astronomers must carefully correct for this effect, learning to read through the dust without mistaking its influence for truth. Closer to home, scattering shapes our own sky. Earth's atmosphere, filled with gas molecules, scatters sunlight in all directions. Blue light, with its shorter wavelength, scatters more efficiently than red. This is why daytime skies glow blue and sunsets burn orange and red. The light has traveled through more atmosphere, losing its blues along the way. Far more extreme obstacles await near black holes. Here, gravity grows so intense that space-time folds inward sharply. When light ventures too close, its path curves endlessly, spiraling toward a boundary known as the event horizon. Beyond this point, all possible paths lead inward. Light does not slow. It does not struggle. It simply has no direction left that leads outward. The journey ends, not with destruction, but with disappearance from the observable universe. Between these dramatic regions lies interstellar space, quiet, cold, and thin, but never empty. There are atoms drifting alone for millions of years before colliding with anything. There are magnetic fields stretching across entire galaxies. There is background radiation humming faintly everywhere. Light moves through all of it, slightly altered, slightly delayed, but never stopped unless captured. Each interaction leaves a fingerprint, a slight shift in color, a tiny loss of intensity, a subtle change in direction. By studying these changes, scientists learn not only about the light's source, but about the invisible terrain it crossed to reach us. In this way, light becomes both traveler and surveyor, mapping space simply by surviving it. It's easy to imagine light as unstoppable, but its resilience comes from adaptability, not invulnerability. It bends, scatters, fades, and yet, enough of it always arrives to tell a story. As you settle deeper into stillness, picture these beams slipping silently past obstacles, curving around gravity, filtering through dust, crossing distances that defy intuition. The universe does not make the journey easy, but light persists anyway. And in the next part of our exploration, we'll open our eyes to the full range of this traveler's many forms, far beyond the narrow colors we can see. For now, let the idea linger. Even the fastest messenger must navigate a complicated path. When we speak of light, we often picture color, soft blues, warm yellows, fading reds. But what your eyes can see is only a thin ribbon cut from a much larger tapestry. The light that fills the universe comes in many forms, spanning an enormous range of energies, all moving at the same unchanging speed. This vast family is known as the electromagnetic spectrum. At one end are long, gentle waves, radio waves, stretching wider than buildings. At the other are gamma rays, so compact and energetic they can pass through solid matter. Between them lie microwaves, infrared, visible light, ultraviolet, X-rays, and more. Different names, different behaviors, yet all are expressions of the same fundamental phenomenon. Visible light occupies only a tiny sliver of this spectrum. Our eyes evolved to detect this narrow band not because it is special in the universe, but because it is abundant and safe on Earth. The sun emits enormous amounts of energy in these wavelengths, and our atmosphere allows them to pass through with minimal harm. What we call normal light is simply what our biology found convenient. Beyond this sliver, the universe glows in ways we cannot directly see. Gamma rays and X-rays pour out from violent regions, supernovae, black holes, colliding neutron stars. These are the signatures of extreme physics, places where matter is compressed, torn apart, or accelerated to astonishing energies. Though invisible to us, these forms of light reveal the universe at its most dramatic. At lower energies, infrared light tells a quieter story. It traces warmth, cool stars, forming planets, drifting dust clouds. All shine most brightly in infrared. What appears dark in visible light often glows richly here, like embers hidden beneath ash. Microwaves and radio waves, gentler still, map cold gas, magnetic fields, and the faint echoes of the universe's earliest moments. Despite their differences, all these waves share the same speed in a vacuum. Whether a photon carries immense energy or barely any at all, it moves through empty space at light speed. The distinction lies not in how fast they travel, but in how they oscillate, how tightly their electric and magnetic fields twist and turn as they move forward. Color itself is a measure of this oscillation. Blue light vibrates more rapidly than red, carrying more energy per photon. Violet sits at the high-energy edge of what we can see, while red marks the low-energy boundary. Step just beyond red, and you enter infrared. Step beyond violet, and ultraviolet begins, light powerful enough to alter molecules and damage DNA. Because each wavelength interacts differently with matter, every part of the spectrum becomes a unique investigative tool. Radio waves pass easily through dust, revealing structures hidden from optical telescopes. X-rays are absorbed by dense material, outlining the shapes of hot, compact objects. Infrared slips through cosmic clouds, exposing newborn stars still wrapped in their dusty cradles. This diversity is why modern astronomy rarely relies on visible light alone. To understand the universe fully, scientists listen to all its colors at once, assembling a layered portrait from many invisible hues. The cosmos becomes richer, deeper, and more complex when seen this way. As you relax, imagine the space around you glowing quietly in countless unseen colors. Waves longer than oceans, waves smaller than atoms, all passing through you, unnoticed, harmless, steady. Light is not just what you see, it is what the universe uses to express itself. And in the next section, we'll watch how this light changes as the universe itself stretches and grows, slowly aging the messages it sends. For now, let the spectrum fade gently into the background, like a rainbow dissolving into night. As light travels, it does not remain unchanged. The universe itself is not still, and neither are the messages carried across it. Space is slowly, steadily expanding, and light, no matter how fast, must stretch along with it. This gentle stretching leaves a subtle mark, one that astronomers have learned to read like the fading pitch of a distant sound. This effect is known as redshift. Imagine a tone drifting away from you, its pitch lowering as distance grows. Light behaves in a similar way. As space expands, the wavelength of traveling light is pulled longer, shifting toward the red end of the spectrum. The energy of each photon gently decreases, not because the light grows tired, but because the space it crosses is growing beneath it. This stretching carries a profound message. The more a galaxy's light is shifted toward red, the farther away that galaxy is, and the earlier in cosmic history we are seeing it. Redshift becomes a kind of timestamp embedded directly into the light itself. Distance and time intertwine, revealed through color. In this sense, redshift is an echo of the Big Bang. The expansion we measure today is the continuation of an event that began nearly 14 billion years ago. Every stretched photon is a quiet reminder that the universe was once hotter, denser, and brighter than it is now. Light remembers that origin, even as it drifts ever farther from it. By measuring redshift, astronomers can map the large-scale structure of the universe. Galaxies arrange themselves into filaments and clusters, vast cosmic webs traced entirely through light that has been gently altered during its journey. Without redshift, much of this structure would remain invisible, its depth flattened into a single plane. Not all shifts move toward red. When an object moves closer, its light is compressed instead of stretched. This creates blue shift, pushing wavelengths toward higher energy. Nearby stars orbiting within our galaxy often show this effect as they move toward us, their light slightly sharpened, slightly energized. These shifts are usually tiny, imperceptible to the eye, yet unmistakable to instruments. Even the smallest change can reveal motion, approach, or retreat across enormous distances. Light becomes a cosmic speedometer, quietly reporting how everything moves. Over immense spans of time, redshift transforms once visible light into something else entirely. Light that began as brilliant ultraviolet radiation in the early universe has been stretched so much that it now arrives as microwaves. What was once blinding has cooled into a faint, uniform glow spread across the sky. As you rest, imagine light growing older as it travels, not fading away, but softening, lengthening, becoming gentler. The universe stretches and light stretches with it, adapting without complaint. In the next part of our journey, we'll meet the oldest light of all, still drifting toward us from the universe's first moments, carrying a memory older than stars. For now, let this slow stretching lull your thoughts, like a long breath taken by the cosmos itself. Long before stars ignited, before galaxies took shape, before darkness and light had any familiar meaning, the universe was filled with a brilliant, blinding glow. Everything was hot. Everything was dense. Light could not travel freely yet. It was constantly scattered, trapped in a thick, opaque fog of particles. The universe, in its earliest moments, was bright but unseen. Then slowly it changed. As space expanded and cooled, a quiet transition occurred. Protons and electrons combined to form neutral atoms. For the first time, light was no longer endlessly blocked. It was released. The universe became transparent, and a flood of radiation began its long journey outward in every direction. That ancient light is still with us today. We call it the cosmic microwave background, or CMB. It is the oldest light we can observe, a relic from a time when the universe was only about 380,000 years old, an infant compared to its current age of nearly 14 billion years. The photons of the CMB have been traveling ever since, drifting patiently through expanding space, waiting to be detected. These photons have traveled for more than 13 billion years to reach us. They have crossed a universe that grew from a hot, compact state into an enormous, structured cosmos filled with galaxies and voids. Along the way, space itself stretched their wavelengths dramatically. What began as energetic, visible, or even ultraviolet light has been softened into microwaves, cool, faint, and uniform. Today, the CMB surrounds us completely. It comes from every direction at once, bathing the universe in a nearly even glow just a few degrees above absolute zero. It is invisible to human eyes, yet detectable with sensitive instruments. Even empty space hums with its presence. This ancient light is one of the strongest pieces of evidence for the Big Bang. No other explanation accounts for its uniformity, its temperature, and its precise spectrum. It is not light from stars or galaxies. It is light from the universe itself, released when everything became calm enough to let photons go free. And yet, within this remarkable smoothness lie tiny imperfections. Subtle variations in temperature, differences of just a few millionths of a degree, are frozen into the CMB. These fluctuations are not noise. They are the seeds of all structure. Slightly denser regions would eventually pull in more matter, growing into galaxies, clusters, and vast cosmic filaments. In this way, the CMB is both an ending and a beginning. It marks the moment light was freed, and it quietly outlines everything that would follow. Every star you see tonight traces its ancestry back to those faint ripples in the ancient glow. As you lie still, imagine these primordial photons passing silently through your body, through the walls around you, through the planet itself. They do not interact much anymore. They simply continue, reminders of a time when the universe was young, simple, and filled with promise. In the next section, we'll shift our focus from the universe's first light to the light of individual stars, each one a small, ongoing echo of that original glow. For now, rest with this thought. Even the oldest memories of the universe are still traveling, still reaching out, still whispering softly into the present. When the first stars finally ignited, they did more than bring light back into a darkened universe. They became storytellers, Each star began sending out a steady stream of photons, carrying information about its inner life, its temperature, its size, its chemistry, and even its age. Long after a star changes or disappears, its light continues on, preserving a version of it that can still be seen. From Earth, this starlight appears to flicker. Stars seem to twinkle, brightening and dimming subtly as you watch. This is not the stars themselves changing, but the result of their light passing through our planet's atmosphere. Turbulent air bends the light slightly from moment to moment, shifting its path just enough to make stars shimmer. It's a reminder that even here, close to home, light rarely travels unchallenged. Because light takes time to cross space, the stars you see tonight may no longer exist. Some burned out thousands or even millions of years ago. Their final photons are still arriving, telling a story that has already ended. In this way, the sky is filled with ghosts, brilliant memories shining long after their sources have faded. The color of a star offers quiet clues. Blue stars burn hotter and live fast, consuming their fuel quickly. Red stars burn cooler and more slowly, often surviving for billions of years. Yellow stars, like our sun, occupy a calm middle ground. These colors are not decorative. They are physical truths, tied directly to surface temperature and energy output. When starlight is spread out into a spectrum, it reveals even more. Dark lines appear where certain wavelengths are absorbed by elements in the star's atmosphere. Each element leaves a unique pattern, a cosmic fingerprint. By reading these spectral lines, astronomers can identify hydrogen, helium, iron, calcium, and dozens of other elements from across the galaxy, without ever touching the star itself. Our own sun holds a surprising secret in its light. Although sunlight reaches Earth in just over 8 minutes, the energy it carries began its journey far earlier. Deep in the sun's core, photons are created during nuclear fusion. From there, they bounce endlessly between particles, scattering and re-emitting, inching outward over hundreds of thousands, perhaps even a million, years before finally escaping the surface and streaming into space. So when sunlight warms your skin, you are feeling energy that began its journey long before human history. It has already lived a long life before reaching you. As you settle deeper into rest, imagine starlight drifting calmly across space, unhurried, patient, faithful. Each beam is a preserved moment, a quiet archive moving forward in time. Next, we'll witness moments when stars do not fade quietly, but end in brilliant flashes, brief, overwhelming bursts of light that reshape the universe around them. For now, let the steady glow of distant suns soften your thoughts, like countless small candles burning far away. Most stars live quietly. They shine, they age, and they fade with little drama. But some stars end their lives in ways so violent, so luminous, that their final moments briefly outshine everything around them. In those rare instances, light becomes overwhelming, flooding space with a brilliance powerful enough to be seen across entire galaxies. These are the explosions we call supernovae. When a massive star exhausts its fuel, gravity finally wins. The core collapses inward in a fraction of a second, and then, almost impossibly, rebounds. A shockwave tears through the star, ripping it apart. For a short time, the light released can rival that of billions of stars combined. A single dying star announces itself to the universe with extraordinary clarity. The light from a supernova carries more than spectacle. Within that blinding flash, new elements are forged. Gold, silver, uranium, many of the heavy elements found on Earth were created in such explosions. The light that escapes bears the signature of this creation, encoding evidence of matter being transformed under extreme conditions. In a very real sense, the atoms in your body were once part of a supernova's glow. Some of the most intense light events in the universe are even briefer. Gamma ray bursts, or GRBs, appear without warning, flare for seconds or minutes, and then vanish. In that short time, they release more energy than the sun will produce in its entire lifetime. Their light is focused, narrow, and devastatingly bright, cutting across space like a cosmic blade. What makes GRBs especially remarkable is how far their light can travel. Some originate so far away that their photons cross more than half the observable universe before reaching us. By the time they arrive, stretched and softened by expansion, they still stand out as unmistakable signals, proof of extraordinary violence at unimaginable distances. Not all stellar explosions are final. Some stars experience repeated outbursts known as novae. These occur in binary systems, where a dense white dwarf steals material from a companion star. When enough matter accumulates, a runaway reaction ignites on the surface, producing a sudden brightening. The system survives only to repeat the process again later. Light flares, fades, and waits. Each of these events reshapes its surroundings. Shockwaves trigger new star formation. Radiation clears out nearby gas. Heavy elements are scattered, enriching future generations of stars and planets. Light does not simply announce destruction, it seeds creation. As you breathe slowly now, imagine these immense flashes happening silently across the universe, far beyond awareness, far beyond urgency. Their light travels calmly, long after the violence has ended, arriving as a gentle signal of something extraordinary that once occurred. In the next section, we'll explore moments when light meets itself, interfering, overlapping, and revealing the delicate wave nature hidden beneath its speed. For now, let these distant explosions fade into quiet memory, their brilliance softened by distance and time. Despite its ability to illuminate vast distances, light is surprisingly delicate. When multiple beams cross paths, they do not collide like solid objects. Instead, they overlap, blend, and interact in subtle ways. Sometimes they reinforce each other. Sometimes they cancel out. This behavior reveals one of light's most quietly fascinating traits, its wave nature. When two light waves meet in step, their peaks align and amplify one another. The result is brighter light. When a peak meets a trough, the waves diminish or even erase each other, leaving darkness. This pattern of reinforcement and cancellation is known as interference, and it lies at the heart of many optical phenomena we take for granted. Telescopes, for example, rely on interference to sharpen their vision. By carefully combining light waves collected from different points, astronomers can enhance detail far beyond what a single lens or mirror could achieve alone. In some observatories, light from multiple telescopes is brought together and allowed to interfere, forming images with astonishing clarity. Diffraction is another quiet consequence of light's wave behavior. When light passes through a small opening or around an edge, It spreads slightly instead of traveling in a perfectly straight line. This spreading creates characteristic patterns, including the soft rings known as airy disks that appear around stars in telescopic images. Even the most precise instruments must work within these gentle limits. Interferometers take this principle to its extreme. By measuring how light waves interfere after traveling along different paths, these devices can detect incredibly small changes, distances smaller than the width of an atom. Such precision allows scientists to measure stellar diameters, detect exoplanets, and even sense ripples in space-time itself. You encounter interference in everyday life more often than you might realize. The rainbow colors shimmering on a compact disk or soap bubble arise from light waves reflecting off closely spaced surfaces and interfering with one another. What appears decorative is, in truth, physics quietly at work. These patterns remind us that light is not just a stream of particles or a straight-line traveler. It spreads, overlaps, and responds to its environment with remarkable sensitivity. Every interaction leaves a faint trace of structure. As you relax further, imagine gentle waves of light passing through one another without conflict, forming patterns that appear and dissolve, like ripples on a calm pond. Nothing crashes, nothing breaks. Everything simply aligns or drifts apart. In the next part of our journey, we'll see how gravity itself bends these waves, turning massive objects into natural lenses that reshape what we see. For now, let the idea of interference settle softly, a reminder that even the simplest beam of light contains hidden complexity. Gravity does not shine. It does not glow or sparkle or announce itself with light of its own. And yet, it quietly reshapes everything light touches. Wherever mass gathers around stars, galaxies, or vast clusters, space and time themselves bend. Light, ever obedient to the structure beneath it, follows these curves without resistance. This is the phenomenon known as gravitational lensing. When a massive object lies between us and a distant source, its gravity warps space-time enough to deflect passing light. The photons do not slow down, and they are not pulled like falling stones. Instead, their paths gently curve, tracing the shape of distorted space. To an observer, the background object may appear stretched, smeared into arcs, or multiplied into several ghostly images. Sometimes the alignment is nearly perfect. In these rare cases, light forms a luminous ring around the intervening mass, known as an Einstein ring. The source galaxy may be far beyond reach, yet its image becomes bright and clear, magnified by gravity alone. Nature builds its own telescopes, far more powerful than anything humans could construct. These cosmic lenses allow us to see farther than we otherwise could. Galaxies that would be too faint or too distant suddenly become visible, their light boosted by the curvature of space-time. In this way, gravity becomes an ally to observation, revealing parts of the universe that would remain hidden in darkness. Gravitational lensing also reveals something even more elusive: dark matter. Though invisible and undetectable by light, dark matter still possesses mass. It bends space-time just like ordinary matter does. By studying how light is distorted, astronomers can map where dark matter must be, tracing its presence through its gravitational fingerprints. On smaller scales, lensing subtly shifts the apparent positions of stars. On larger scales, entire clusters act as vast optical systems, distorting the background universe into intricate, flowing patterns. The images appear dreamlike, almost painterly, evidence that space itself is not rigid, but fluid. As you rest now, imagine light drifting calmly through these warped regions, curving gracefully, never resisting, never complaining. It adapts to every bend in reality, carrying its message faithfully along whatever path space-time provides. In the next section, we'll listen to a different kind of light, radio waves, traveling quietly through dust and darkness, revealing a universe invisible to our eyes. For now, let gravity's gentle shaping fade into the background, like a slow current guiding unseen travelers through the deep. Not all light arrives as brightness to the eye. Some of it comes quietly, stretched into long, gentle waves that pass through matter almost unnoticed. Radio waves are among the calmest travelers in the electromagnetic family, carrying information across space with remarkable persistence. Where dust blocks visible light, radio waves slip through, unbothered, continuing on their steady course. Because of this, radio astronomy opens a very different window onto the universe. Vast clouds of gas that appear dark in optical images glow softly in radio frequencies. The structure of galaxies becomes clearer. Invisible magnetic fields reveal themselves through subtle patterns in radio emissions. The universe begins to look less like a collection of bright points and more like a living, breathing landscape. Some of the most mysterious signals ever detected arrive this way. Fast radio bursts, brief flashes lasting only milliseconds, appear suddenly from distant galaxies and vanish just as quickly. In that fleeting moment, they can release as much energy as the sun emits in days. Their origins remain uncertain, but their precision and power suggest extreme environments, possibly involving neutron stars or other exotic objects. Then there are pulsars, dense remnants of massive stars that spin with incredible regularity. As they rotate, they sweep narrow beams of radio waves across space like cosmic lighthouses. Each time the beam crosses Earth, we detect a pulse. Some pulsars are so precise that they rival atomic clocks, their steady rhythm marking time across the galaxy. Radio waves also play a central role in one of humanity's quietest searches. Through programs like SETI, scientists listen patiently for patterns that might suggest intelligent origin, signals that stand out from natural noise. So far, the universe remains silent in this regard. But the listening continues, gentle and persistent. When the sky is mapped in radio frequencies, it looks nothing like the familiar star-filled view. Entire regions glow where nothing is seen in visible light. Structures emerge that hint at processes unfolding slowly over millions of years. As you breathe slowly now, imagine these long waves passing through you, through walls, through the earth itself, harmless, invisible, steady. They have crossed galaxies, survived dust and distance, and arrived without urgency. In the next part, we'll return to a familiar idea with new understanding. Light as a natural time machine, revealing not where the universe is, but when it was. For now, let the radio sky hum softly in the background, a quiet chorus beneath the stars. Light does more than illuminate space. It quietly rearranges our understanding of time. Because it travels at a finite speed, every observation we make is also a look into the past. Telescopes, in this sense, are not just instruments for seeing far away. They are natural time machines, tuned to different depths of history. When astronomers observe a galaxy 100 million light-years away, they are seeing that galaxy as it existed 100 million years ago. The stars may have shifted. The shape may have changed. Entire generations of suns may have lived and died since the light we now collect first began its journey. The image arrives intact, but outdated, a preserved moment drifting forward. This means something quietly unsettling. There is no way to see the universe as it is right now. Every direction we look leads backward in time. The farther we look, the deeper into the past we go. Even the light from the moon is slightly delayed. Even sunlight is already 8 minutes old by the time it reaches your skin. Time, then, is layered around us like a shell. Nearby space shows us the recent past. Distant space reveals ancient eras. The universe becomes a vast archive arranged not by location, but by age. There is a limit to how far this archive extends. Beyond a certain distance lies the edge of the observable universe, not because nothing exists beyond it, but because light from those regions has not had enough time to reach us since the beginning of cosmic expansion. Those parts remain causally disconnected, silent for now. Light also enforces a universal speed limit on information itself. No message, no signal, no influence can travel faster. Cause must always precede effect. This rule keeps reality consistent, preserving order across unimaginable distances. As you rest now, imagine time unfolding not as a straight line, but as a gentle gradient of memories surrounding you. Every photon arriving carries a timestamp, a quiet record of when it was created. In the next section, we'll explore light that does not come directly from its source, but arrives by reflection and scattering, soft echoes shaped by surfaces and particles along the way. For now, let the idea settle. To see is to remember, and every act of observation is a conversation with the past. Not all light reaches us straight from its source. Much of what we see is light that has already touched something else, reflected, scattered, softened along the way. These indirect journeys give the universe a gentler glow, shaping familiar sights and subtle wonders alike. Moonlight is the simplest example. The moon does not produce its own light. It quietly reflects sunlight back toward Earth, its surface scattering photons in many directions. What appears silver and calm in the night sky is, in truth, borrowed light, sunlight that has taken a short detour before arriving at your eyes. Planets behave similarly, and this is why they appear steadier than stars. Unlike distant stars, which act like tiny points of light, planets present small disks. Their reflected light averages out atmospheric turbulence, so they shimmer less. The calm glow of a planet is not a sign of stillness, but of reflected geometry. Farther away, reflection becomes more dramatic. Saturn's rings shine brilliantly because they are made of countless icy particles. Each fragment scatters sunlight, and together they form one of the brightest structures in the solar system. The rings glow not from heat or fusion, but from billions of tiny mirrors drifting information. In the depths of space, entire clouds of gas and dust reflect or emit light in different ways. Reflection nebulae shine by scattering nearby starlight, often appearing blue because shorter wavelengths scatter more efficiently. Emission nebulae, on the other hand, glow from within, energized by nearby hot stars that excite their atoms, causing them to emit light of specific colors. Closer to home, light scattering paints Earth's skies. During twilight, sunlight travels through more atmosphere, scattering blues away and leaving reds and oranges behind. The sky becomes a gradient of warmth, a daily reminder of how light changes when its path grows long. And sometimes, light arrives not from reflection or scattering, but from interaction. Auroras shimmer near Earth's poles when charged particles from the sun collide with gases in the atmosphere. Oxygen and nitrogen glow briefly, creating curtains of green, red, and violet that ripple silently across the sky. It is light born from collision, brief and beautiful. As you settle deeper into stillness, imagine these soft echoes of light: sunlight borrowed by moons, stars mirrored by dust, energy transformed into color high above the earth. Light rarely travels alone. It touches, it changes, it returns altered but still faithful to its origin. In the next section, we'll step into one of light's deepest mysteries: its ability to behave not only as a wave, but as a particle, blurring the boundary between energy and matter. For now, let these reflections fade gently, like moonlight dissolving into dawn. For much of history, light seemed easy to describe, traveled in straight lines. It reflected from mirrors, it bent through glass, and yet, as scientists looked closer, light began to behave in ways that refused simple explanation. Sometimes it spread like a wave across water. Other times it arrived in tiny, indivisible packets, as if it were made of particles. Both descriptions were correct and incomplete on their own. This dual nature is one of light's most quietly astonishing traits. In some experiments, light behaves unmistakably like a wave. It interferes with itself, spreads through narrow openings, and forms delicate patterns of brightness and darkness. In others, it acts as a stream of particles called photons, each carrying a precise amount of energy. These photons arrive one by one, striking detectors in discrete events, never as half measures. Rather than choosing one identity, light exists comfortably as both. A photon carries no electric charge. Because of this, it passes through magnetic fields unaffected, gliding along without being deflected. This neutrality allows light to cross vast regions of space where charged particles would be trapped, twisted, or slowed. Photons move freely, guided only by gravity and the structure of spacetime itself. Despite having no mass, photons still carry momentum. When light strikes an object, it exerts a tiny pressure. This pressure is almost imperceptible in everyday life, but in the vacuum of space, over long periods, it becomes meaningful. Engineers have even designed spacecraft concepts called solar sails, which use sunlight itself as propulsion, slow, gentle, and continuous. Your own eyes are exquisite photon detectors. Every moment of vision begins when photons enter the eye and are absorbed by specialized cells in the retina. Each absorbed photon triggers a chemical reaction, converting light into an electrical signal that your brain interprets as sight. Seeing, at its core, is a direct interaction between individual particles of light and living tissue. Modern cameras operate on a similar principle. In low-light conditions, advanced sensors can detect and count individual photons. Images emerge gradually, built particle by particle until a coherent picture forms. Even in near darkness, light leaves a trace. As you rest now, imagine photons drifting quietly toward you, not as beams or waves, but as tiny, punctual messengers. each one arriving with a precise amount of energy, each one completing a journey that began long ago. In the next section, we'll follow some of the longest and loneliest journeys light ever makes, crossing millions or even billions of years before finding a listener. For now, let the idea settle gently. Light does not need to choose what it is. It simply is both wave and particle, both motion and message. Some journeys are so long that they defy ordinary imagination. Light undertakes these journeys without hesitation, crossing distances measured not in kilometers or miles, but in millions and billions of years. These are the longest paths any messenger can take, and yet light completes them with quiet consistency. The most distant galaxies we can observe send us light that has traveled for more than 13.4 billion years. Those photons began their journey when the universe was young, when galaxies were smaller, brighter, and closer together. Since then, space itself has expanded beneath them, stretching their paths and softening their energy. By the time they arrive, they are faint and red, but unmistakably ancient. Closer to home, even our own machines experience this delay. Voyager 1, now far beyond the outer planets, sends radio signals that take over 22 hours to reach Earth. Each message is a snapshot of where the spacecraft was nearly a day ago. Communication becomes a conversation with the past, paced by the speed of light. Between Earth and Mars, the delay is shorter but still noticeable. Depending on their positions in orbit, signals can take anywhere from 4 to 24 minutes to cross the gap. Commands are sent. Silence follows. Only later does confirmation arrive. Space insists on patience. Within our own galaxy, distances stretch even further. Light requires roughly 100,000 years to cross the Milky Way from edge to edge. Every star you see is embedded within this slow, luminous circulation of information, each one broadcasting its presence across a timescale far longer than human history. This delay creates a strange possibility. If a civilization exists 65 million light-years away, their telescopes would currently show Earth as it was during the age of dinosaurs. They would see forests untouched by cities, oceans without ships, skies without satellites. To them, humanity has not yet appeared. As you settle deeper into rest, let these immense distances soften your sense of urgency. Light moves quickly, but the universe is vast, and even the fastest traveler takes its time. In the next section, we'll explore how scientists translate invisible light into color, creating the familiar images that shape our vision of the cosmos. For now, imagine these long journeys continuing quietly, uninterrupted, across the deep. When we look at images of the universe, we often assume we are seeing it as it truly appears. Brilliant blues, glowing reds, delicate golds drifting through darkness. Yet much of what we see is not color in the human sense at all. It is translation, a careful, thoughtful conversion of invisible light into something our eyes can understand. Much of the universe does not shine strongly in visible wavelengths. Some regions are too cold. Others are wrapped in thick clouds of dust. Still others emit most of their energy far beyond what human vision can detect. To reveal these hidden structures, astronomers use false color, not to deceive, but to clarify. False color assigns visible hues to wavelengths outside our natural range. Infrared might become red or gold. X-rays may appear blue or purple. Radio waves might be rendered as soft greens or reds. Each color is chosen deliberately, allowing patterns, temperatures, and compositions to stand out clearly. The result is not what the eye would see, but what the data is saying. The Hubble Space Telescope, famous for its breathtaking images, often begins with black and white photographs. Each image captures light through a specific filter, isolating a narrow wavelength. These separate layers are then combined, colorized, and balanced, revealing details no single exposure could show alone. Color becomes a language, not a decoration. Because of this process, nebulae do not appear exactly as shown in photographs. The towering pillars, glowing clouds, and intricate filaments are real structures, but their colors are interpretive. They highlight hydrogen, oxygen, sulfur, each assigned a color that helps scientists distinguish one from another. The beauty is authentic, even if the palette is symbolic. False color is a powerful scientific tool. It allows astronomers to identify chemical elements, trace energetic processes, and map temperatures across vast regions. What might look like art is, in fact, analysis rendered gently visible. The James Webb Space Telescope continues this tradition in a new domain. Webb observes primarily in infrared light, capturing the faint warmth of distant galaxies and newborn stars. Its images begin as data, numbers describing intensity and wavelength. Those numbers are then carefully translated into color, giving us scenes that feel rich, deep, and almost dreamlike. As you relax now, imagine the universe glowing in countless unseen shades, layered far beyond what eyes alone can capture. What we call color is only a small window into a much larger conversation carried by light. In the next section, we'll meet some of the strangest and brightest sources of light in existence, objects so extreme that they bend our understanding of physics itself. For now, let the colors fade gently, knowing that behind every image lies a deeper spectrum, quietly waiting to be revealed. Some of the brightest lights in the universe do not come from stars at all, but from regions where gravity dominates everything else. At the centers of many galaxies lie objects so powerful that they reshape space, time, and light itself. These are quasars, extraordinarily luminous cores fueled by supermassive black holes. A quasar is not a single object, but a process. Matter spirals inward toward a black hole, forming a glowing disk heated to incredible temperatures. As this material accelerates and collides, it releases vast amounts of energy in the form of light, often outshining the combined glow of all the stars in its host galaxy. From billions of light years away, a quasar can still appear as a brilliant point in the sky. The light from quasars is especially valuable to science because of how far it travels. Along its journey, it passes through intergalactic space, interacting with clouds of gas scattered between galaxies. Each interaction leaves subtle absorption lines in the quasar spectrum. By studying these lines, astronomers learn about the otherwise invisible matter filling the vast spaces between galaxies. Black holes themselves remain unseen. They emit no light from within their event horizons, but their presence is undeniable through the way they influence nearby matter and light. Stars orbit unseen centers. Gas heats, glows, and spirals inward. Light bends sharply near the boundary where escape becomes impossible. The event horizon marks a quiet but absolute limit. Once light crosses it, all possible paths forward lead deeper in. No signal can return, To the outside universe, the light simply vanishes. Not destroyed, just removed from communication forever. Yet even black holes can produce light indirectly. Some launch enormous jets of energized particles from their poles, extending thousands of light years into space. These jets shine brightly across the electromagnetic spectrum, tracing magnetic fields and extreme physics at work near the edge of the unknown. As you rest now, imagine light skimming close to these regions, curving sharply, accelerating, then either escaping to tell its story or disappearing silently beyond the horizon. In the next section, we'll step back from these extremes and explore a gentler connection between light and life itself. How illumination shapes biology, evolution, and the search for living worlds. For now, let these distant beacons fade into the background, their brilliance softened by distance and time. Light is not only a messenger of distant worlds, it is also a quiet architect of life. On Earth, nearly every ecosystem traces its energy back to a narrow band of sunlight, filtered gently through atmosphere and water. This specific range of light, neither too energetic nor too weak, made life as we know it possible. Plants, algae, and certain bacteria rely on photosynthesis, a process tuned precisely to visible light. Using photons, they convert carbon dioxide and water into sugars, storing solar energy in chemical bonds. The color green dominates much of the living world because chlorophyll reflects green wavelengths while absorbing reds and blues, the most useful for driving this ancient reaction. Over time, life adapted to the light that was available. Earth's atmosphere blocks much of the sun's dangerous radiation, especially X-rays and most ultraviolet light. What remains is a safe optical window, and within it, vision evolved. Eyes are not random inventions. They are finely tuned instruments shaped by the spectrum that reaches Earth's surface most reliably. Yet ultraviolet light still plays a complex role. In excess, it damages DNA, breaking molecular bonds and causing mutations. But in moderation, it enables the production of vitamin D, essential for bone health and immune function. Light, once again, is neither good nor bad. It is powerful, and balance matters. In the depths of the ocean, far from sunlight, some organisms solve the problem differently. They create their own light. Bioluminescent creatures, jellyfish, squid, plankton, produce soft glows through chemical reactions in their bodies. These lights attract prey, deter predators, or communicate in darkness where vision would otherwise fail. Life learned not only to use light, but to invent it. Beyond Earth, light becomes our primary tool in the search for life elsewhere. When astronomers study distant exoplanets, they analyze the light passing through or reflecting from their atmospheres. Certain combinations of gases, oxygen, methane, water vapor, can hint at biological activity. Life, if present, leaves subtle fingerprints in light. As you rest now, imagine light nurturing forests, feeding oceans, guiding eyes, and whispering clues about life beyond our world. Connects biology to the cosmos, grounding living systems in stellar energy. In the next and final sections, we'll turn toward humanity's tools, how we capture distant light, and then gently wind down, reflecting on what these traveling photons truly mean. For now, let this thought settle softly. Every breath you take is linked, in some distant way, to the quiet work of light. For most of human history, light from the universe arrived silently and passed unnoticed. Stars rose and set. Planets wandered. Only with patience and curiosity did we begin to build tools to catch those distant photons before they faded away. The earliest telescopes were simple, long tubes with glass lenses that bent light just enough to magnify the sky. They revealed moons around Jupiter, rings around Saturn, and countless stars hidden from the naked eye. Each improvement in glass and alignment allowed more ancient light to reach human vision. But Earth's atmosphere, while protective, is also restless. Turbulent air blurs starlight, making distant objects shimmer and soften. To escape this distortion, humans place telescopes in orbit. Above the atmosphere, space telescopes receive light in its purest form, sharp, steady, and undisturbed. Different kinds of light require different tools. Visible light can be focused with mirrors. Infrared detectors must be cooled to near absolute zero so they do not glow themselves. X-rays cannot be focused easily at all and must be guided at shallow angles. Each wavelength demands patience, engineering, and quiet precision. Radio telescopes listen rather than look. Their giant dishes collect long wavelength light that passes through dust and gas untouched. When many antennas work together, spread across continents, they form a single virtual telescope the size of Earth. This technique allows astronomers to resolve details finer than any single instrument could achieve. Some observatories do not even detect light directly. Gravitational wave detectors like LIGO measure tiny ripples in spacetime caused by distant cosmic collisions. In a way, they extend astronomy beyond light, yet still confirm what light has long hinted at. The universe is active, dynamic, and deeply interconnected. As you drift deeper into rest, imagine humanity quietly waiting beneath the stars, building ever more sensitive instruments, learning to listen carefully to ancient light that has crossed unimaginable distances just to arrive. In the final section, we'll step beyond technology and into imagination, where light meets our dreams of travel, connection, and understanding. Let the instruments fade now. The universe continues shining, whether we watch or not. Light has always set the ultimate speed limit of the universe. No message, no object, no cause can outrun it. And yet, human imagination has never stopped wondering what lies beyond that boundary. In science fiction, warp drives bend space itself, shortening the distance rather than breaking the rule. In theory, space-time could stretch behind a vessel and compress ahead of it, allowing effective faster-than-light travel without locally exceeding light speed. For now, this remains mathematics and speculation. Beautiful, quiet ideas waiting for evidence. Wormholes offer another dream. Hypothetical tunnels through space-time, connecting distant regions like folded pages in a book. If they exist, light could pass through them along a shortcut, arriving far sooner than expected. But such structures, if real at all, would require conditions far beyond our current reach. Quantum physics introduces even stranger concepts. Entangled particles seem to share information instantly across vast distances. Yet no usable message travels this way. Light still holds its role as the universe's fastest storyteller. And so we return to what is real and present. Every photon that reaches your eyes tonight has survived collisions, dust, gravity, and time itself. It traveled faithfully, never speeding up, never slowing down, carrying information from its source to you. To study light is to study history, To observe the universe is to read messages written long before humans existed. Galaxies forming, stars dying, atoms cooling, all preserved in motion, waiting to be noticed. As you rest now, imagine those photons finally completing their journey, ending not in instruments or equations, but in quiet awareness. Their stories do not rush. They arrive gently, one by one. And perhaps that is the final fact worth remembering. Every beam of light that reaches you is patient. Every glow is ancient, and we are only just beginning to understand the stories they tell. Let the light fade softly now. Sleep comes next,